MOSFET transistor. We finished up to finding the transconductance and finding the channel and modulation resistance or not. Okay, so today we'll finish that small signal modeling. Okay, so we found GM. Sorry. We found the GM. Okay, three formulas are GM and R0. R0 equal to 1 by lambda ID. Okay, so this is the small signal equivalent model of MOSFET. Now, we want to include one more effect, body effect. So R0 due to channel length modulation. Okay, GM we all know the ideal MOSFET is a voltage control current source. So voltage control current source. This is ideal thing. Non-ideality channel and modulation R0. So finite R0 there. Ideally R0 should be infinite. Due to non-ideality, okay, that means channel and due to channel and modulation, current is not constant. So we include R0 effect. So what is other non-ideality? Body effect. So you know body effect will vary the threshold voltage. So due to varying threshold voltage, there will be additional current, but in terms of small signal model, additional small signal current. So how to represent body effect in this small signal model? So you know body effect means source bulk voltage. Okay, since in small signal model we analyze with respect to the source, all the voltage we are analyzing with respect to the source terminal because source terminal is grounded. That is a lower node. But this is a reference node we are using. Okay, so source bulk voltage also in terms of source bulk we can call it as body because we are applying the small signal at body. So we can say it as body voltage with respect to the source. We are applying some body voltage with respect to source. How the behavior in terms of small signal. Okay, so that you can see body chain. Okay, it will introduce a current. So introduce a current means transconductance. So the corresponding term is GMB. GMB means transconductance. GMB means transconductance due to body effect. But so GMB vary the body source. How the current will change? Dou ID by dou BS. So what is GM? What is GM formula? Dou ID divided by what will come here?
Dou VGS.
VGS. Right? Now we are applying body, so dou ID divided by VBS. The corresponding transconductance parameter is GMB. V refers body. Applying the body voltage. Okay. So you know the current expression for ID. Okay, so let me write here. Dou by dou VBS. Saturation. So of mu n C ox W by L VGS minus VGS square. Here, which parameter depend on the body source voltage? VGS or VTS? Which parameter?
VTH.
VTH. Right. So let's take differentiating. 2 will come here. 2 getting cancelled. So mu n C W VGS minus VTH. This is a common. The internal VTH is a dependent thing. VTH. So minus dou VTH. Differentiate dou VTH respect to the body source voltage. So you know the VTH formula. Okay, so you know body effect that formula there no. Now it is I'm searching. Yeah. Okay, VTH4 plus gamma into root of 2 pi a plus VSB minus root pi a. Okay, so I want to dou VTH with respect to dou VBS. You can differentiate it on your own. So let me miss that thing. Okay, so when you differentiate it, okay, or into I can because VTH in terms of VSB, so VBS I can write minus VSB, the negative sign will come. So when you differentiate, you will get this thing. Fine. So dou VTH will be distinct. So let's substitute this expression here. Okay, so you know this term is mu n C of W by L VGS minus this is GM. Am I right? This term is GM. So finally I can write GMB equal to GM into gamma divided by this term. Okay, so this thing I can simply write eta, some constant term eta. So GMB equal to eta into GM because everything constant. Gamma is constant, phi f is constant, VSB is a known voltage. But everything constant, I can write eta equal to GM. So now you understand GMB equal to eta into GM. So here eta is always lesser than 1. Okay, so eta is always lesser than 1. Okay, so that means body effect transconducting, it is some some multiplier of GM. That multiplier is very small. Right? So it's something like a fraction of GM. Okay, GMB is some fraction of GM. That means GMB is lesser than. It is very small value. Right. Okay, so how to represent this GMB in this thing? Okay, so what is GMB? GMB with respect to the body source voltage. So how can I write? Okay, so GM how we represent? How will you represent in terms of dou ID? Dou ID equal to GM into del VGS. I can write del VGS small VGS. So that's what GM into small VGS. Similarly, GMB also I can write. Okay, so it applies. So what is GMB? Dou ID by dou BS. So dou ID equal to GMB into small VGS. So small body to source voltage. So I can represent in this way. It is also flows from drain to source. So GMB into small VBS. Here VBS not a large signal, very small thing. I can think like small VBS, small signal. Right. So this is a thing due to body effect. We include the GMB term here. So this is a final small signal model. Okay. The ideal voltage control current source, channel and modulation resistance, then the current conduction due to the body effect. So you can see GM, GMB are in the same direction. For GM, the applied voltage is VGS. For GMB, applied voltage is body to source voltage. Fine. So this is a small signal without capacitances. We didn't add any capacitance. This is simply a static model, but without applying any considering any capacity effect. Okay, when you come take into capacity effect, the final small signal model is okay. So gate to source, one capacitance there. Similarly, gate to drain, one capacitance will be there. Where the gate to drain. So what are the capacitance we are having? CGS, CGD, okay, CDB, CSB. Then what are the remaining? CSB, CDB, and gate to bulk. You know, when transistor is off, there will be gate to bulk capacitor. So all the capacitance can see. CGS is there. Okay. Then CGD there. CD to bulk. You know, this is a bulk terminal because we are applying the bulk terminal here. Back gate. That's what back gate. Right. So C drain to bulk, C source to bulk, then C gate to bulk. So this is a overall small signal model of the MOSFET transistor. So when you studying about amplifier, okay, we need to represent the MOSFET in terms of this small signal model. Okay, so in second module, we'll analyze MOSFET at low frequency. So at low frequency means capacitance won't come. Capacitance will come into picture only at high frequencies. So first we'll study about the low frequency behavior without the capacitance. Then we'll go to second unit frequency response. So with the capacitance, how the response of amplifier will be. Okay, so when the capacitance will come, bandwidth will come. Okay, first analyze in terms of low frequency. Low frequency means only distinct. So this is a low frequency small signal model. Yes, sir. But this is a high frequency small signal model. Okay, what is simply low frequency? Simply DC. Low frequency means DC. Fine. Okay, so that's all about the small signal model. Okay, so with this thing, today we'll start the module 2 common source amplifier. So before going to the amplifier, okay, so we see what is basically the small signal, what is basically amplifier. Okay, so where we have to apply the small signal modeling. You can see when you apply input, output is linearly varying. Okay, so that means this is a relation, linear relation. But practically, due to non-idealities, okay, the amplifier won't be linear. So there will be some non-linear terms will be there. So the practically non-ideal curves will be there. So what you want to do, we want to operate our transistor only in this, where that the amplification is linear. But we cannot operate here. Why? It is non-linear. Okay, here only when you apply very small signal, the behavior is linear. So we want to operate our transistor in this Q point, where okay the response is linear response. We are interested here. So here we can apply small signal model. Yes. You know, small signal model is a LTI equivalent, linear time invariant equivalent. But such that there is no non-linearity will be there. Okay. So now when you take analog, when you analyzing the analog circuit, there are multiple performance metric we need to consider. The first one is gain. What is the second thing? Speed. Remaining control next thing. So then how much power dissipation should be, how much in an input and output impedance should be. Okay, so what is the noise? Okay, that is also important. Noise, linearity. So when you design in particular analog circuit, so we need to consider multiple performance metrics. So we cannot say we cannot always get a high gain. Okay, so sometimes high gain, maybe power dissipation will be high, or sometimes high gain, maybe input impedance must be low. Okay, so we cannot say always, we cannot say one parameter should be dominant than another. So there should be trade-off between the parameter. Right? We want moderate gain with moderate noise or low noise. One parameter cannot dominate. So there will be some trade-off between the each parameter, because gain, if you are increasing one parameter to increase the gain, that will affect the other parameter. So there should be a trade-off. We should target for the optimum performance. So designing analog circuit, it's in digital you might have studied. Okay, you remember? And you okay? Let me write here. Close. Over time. Yeah. Okay. So digital you might have studied. Okay. Digital either you will concentrate on low power or high speed. You can see only this kind of thing. Either the performance will concentrate on low power or high speed. But analog will target only for the optimum performance. Right? So digital only we will target about the high end like that. Better thing. Analog, okay, you want moderate power, moderate speed, better gain. But so analog, the designing is completely different from the digital thing. Because in analog, if you touch gain to increase, other parameter will get affected. There should be trade-off between the each of the parameter. So that's the objective. Analog design trade-off. Fine. So with this thing, now we'll come to the common source amplifier. Fine. So in BJT, okay, you might have studied common emitter, common base, common collector. So equivalently in MOSFET, corresponding to common emitter is common source. Okay, so first we'll start from common source. Next we'll go to the common base means common gate. Common collector means common drain. But this is the equivalent thing comparing to the BJT. First we'll start from common source amplifier. So common source means why it's called common source. Anyone can answer why it is called common source? Okay, let me.
Source is common to both.
Source is common between
input terminal and output terminal.
Okay, so okay, source is common to
Input port and output port.
good. Input port here, output port here, So input voltage with respect to the source, output voltage with respect to the source. So source is common. So that's what this topology is called as common source amplifier. So in common source amplifier, we apply the input at the gate, observe the output at the gate. Fine. So input is voltage. What is output? Voltage or current?
Current.
Current. Because why current? MOSFET is a voltage control
Current source.
current source. GM into VGS. So input is V in is VGS. What is the current here? And let's take small signal. ID equal to GM into VGS. So that's what you can say. MOSFET equivalent circuit. I'm applying gate to source voltage. Fine. Gate to source voltage. You know, MOSFET. There is no. What is a okay? Let me finish this thing. GM into VGS. This is a gate terminal. Fine. This is a drain terminal. GM into VGS. Fine. Here ground. What is the equivalent circuit in BJT? Let's take. I'm taking here base. Yeah. Okay. Collector. So this is a emitter. Okay. Emitter. I'm grounding here. Emitter. So GM. This is base emitter voltage. GM VB. Fine. BJT. What is additional component will come? Anyone can answer?
R pi, internal resistance.
R pi. Why R pi there? What is R pi formula?
Because resistance is not infinite.
What because?
Because
because
input
input-
That is fine.
resistance is not.
So you know in BJT always some finite base current. What is gate current in MOSFET? Zero.
Always
What is
zero.
base current? In BJT always some non-zero current is there. To introduce non-zero current, we introduce R pi. But in MOSFET, there is no gate current, so input impedance is infinite. So that's a good thing. Right? So in BJT, R pi will include MOSFET. There is no that means input network. There is no resistance. Fine. So now this is the equivalent thing. Okay. So now current is voltage is converted to the current. Fine. Now we'll come to the common source amplifier. So this is the thing. Now I want to convert here ID. I want to convert into voltage. How can I convert current to voltage? Here current is available. How can I convert to voltage?
By a load.
By
Like-
load. Load. Alright. Then current will flow here. Voltage will be come. V equal to R. Fine. So that's what RD. Here load is RD, gain resistance. You understand? Because small signal perspective, VDD will become ground. Am I correct? So current will flow to the ground voltage. Because source is a reference node, VDD will become ground. So source and reference node is same, both are ground. Fine. So this is a common source amplifier. Fine. So first, before going to the small signal modeling to derive the gain, first we'll analyze large signal analysis. That means applying different inputs. Okay, we'll analyze the operating region. Okay, so like triode, saturation. Okay, then cutoff. Okay, so then which region we need to operate? From that we will derive the gain expression from the large signal equation. Then we'll go to the small signal model. Okay, so first we'll start the large signal model. Okay, I'm applying V in from 0 to higher value. Varying V in. Okay, so let me. I'm varying V in from lower to the higher value, 0 to higher value. Fine. First V in is low. Transistor is off. Off means no current. So Vout simply equal to VDD. Okay, here M1 is equal to. Fine. So initial drain voltage is VDD. Okay, initial drain voltage is VDD. Now, if I increase V in, when VGS, okay, V in means here VGS. Okay, when VGS is equal to VTS, transistor is on. Okay, so M1 is equal to on. Okay, so what is the operating region? Okay, for deciding operating region, we need to think about VGD or simply VDG. Okay, so let me. Okay, so I'll think about the VGD. So what is gate voltage? Let's take VTH. What is drain voltage? At a point, it is VDD. It should be lesser than threshold. Whether it is lesser than threshold?
Yes, sir.
Yes, or else
Yes, sir.
I will come other perspective. This is if it is confusing. Let me. Okay, I'm okay. This is understandable. So I will erase this thing. I'm coming here. Not here. I'm sorry. I'm coming here. VD should be greater than VG minus VTS. Okay, let's take this point. This is approximately VD equal to VDD. V out. Fine. Greater than what is VG threshold? So 0. Fine. Because drain voltage significantly higher than the gate voltage. Fine. You can see drain voltage significantly higher than gate voltage. So definitely it is in saturation. Fine. So the transistor is not, it is in saturation. Okay. So when keep on increasing at one point VGD. So what is this condition? This condition is called VGD less than VTG. Okay. At one point VGD will become equal to VTS. Fine. So gate voltage, drain voltage will become equal. After that, gate voltage will become much higher. Transistor will become triode region. Okay, so this is a edge of triode region. VGD equal to VTS, it is a edge of triode. Beyond that, gate voltage increasing, transistor will become triode. Is it understandable? Any doubts here? Yes. Okay. So now let's take in this saturation region. What is the current expression? Saturation current expression. Okay. So how can I write V out here? Okay. So V out equal to VDD minus ID into this current is ID. So minus ID into R rate. So in saturation region, what is the current? This thing of mu n C R W by L VGS minus VDS. So ID is this thing. So I can write in this portion, I can write a current like this. Okay, so whatever can I write current expression in triode region? How the current expression might be? Saturation region means ID equal to mu n C R W by L VGS minus VTH whole square. How can I write in triode region current expression? Yes.
Mu and COX W by L VGS minus VT VDS minus
VGS
VT
minus VTH into VDS minus VDS square by 2.
Radius
Am I
square
right?
by 2. Yes, sir.
Okay, some authors will write, okay, in terms of writing, they will write mu n C of W by L. VDS they will take outside. VGS minus VTH minus VDS by 2. You can remember any one of the thing. Right? So in triode region, you can write like this. Right? So you can see you can bring the off here. So VGS minus VTH into VDS is V out. Fine. VDS is V out. Fine. Sorry. VDS is V out minus it. That's what V out minus VS square divided by 2. Fine. So you can bring the 2 here. This 2. Okay. Let me write here. I bring the 2 inside. V in minus VTH into V out minus VS square divided by 2. The same formula what I have done. Here V out is VDS. Fine. So this is the equation for the in this region beyond A. V in greater than V in 1 in triode region. Fine. So now all of you know in triode region we can approximate a transistor in as a resistor. But what is approximation? When that approximation will be valid? What is the condition for it? Okay, let me do that thing. Anyone of you found Ron? Please let me know. I am searching for it. Please come. You can see Ron when it will be valid, VD is very lesser than 2 over time. That means in terms of here, how can I write? So BDS should be very lesser than 2 into BGS minus VTS. What is VDS here? V out. What is VGS here? Vin. 2 into Vin minus VTS. So for this condition, we can approximate in triode region, we can approximate this transistor as a resistor. But so for this condition, so I can approximate as a resistance Rn. So what is the Rn formula? 1 by mu n
1 by mu n
C of
COX
W by L into
VGS
V
minus
out or VGS minus VGS is V in. Okay. I am writing that. V in minus VGS. Okay, so I can approximate resistor. So what is V out now? Okay, so what is V out now? So can I write this thing? So V in. Okay, this is logical model, so I cannot think. Okay, so VDD into Rn divided by Rn plus RD. That is V out. Okay, so you don't worry about this expression because we are only interested in saturation region. We are not interested in operating time, but approximately we can think like that. So you can see finally it will become very it's almost constant. So that's what you can see. Curve will become almost constant. Fine. So now we will come to, so we analyze the different region of condition, saturation region, what is the current expression and voltage expression, then triode region, what is the current expression, corresponding voltage expression, and at very high input, we can approximate our MOS transistor in as a resistor, so what is the corresponding Vout expression. So up to this large signal behavior over. Okay, so now our objective is we want to operate our transistor here, saturation region. Okay. We want to operate our transistor here. Fine. So here only the gain will be there. In triode region, gain will be low. Why the triode region gain will be low? What's the reason? Yes. Why the triode region gain will be low? See this curve. In triode region, GM is decreasing. In saturation region, GM is high. It is always constant. So we want to operate our transistor. We want more gain means more transconductor. Because what is transconductor? Applying gate voltage, current will get current amplification. That's what GM into VGS. Okay, so this is MOSFET is a voltage controlled current source. Current means what? Transconductor. Output is a current. Right? So that's what we are operating.
Sir, what is VB in this
Yes.
curve?
Yes.
Sir, what is VB in this curve?
V
VB.
VDS. But DVDS is a gain to source. 1 plus lambda VDS we are saying no, without channel and modulation effect. But so you know in triode region, GM is proportional to VDS. Okay, so let me write here. Write it very clearly. In saturation, what is GM? Can you tell me in GM? Mu n
Mu n
C of
COX W by L.
L VGS
VGS minus
minus
VTH.
Fine. So in triode region, fine, you can derive this formula. So GM equal to mu n C of W by L VDS. Fine. You can see in saturation region, okay, it is whatever VDS we vary, okay, it is always constant. In triode region, You can see depends on VDS. That's what GM is always not constant and it is also decreasing. Fine. So that's what we want to operate our transistor in saturation region because more GM is there. Right? So we want to operate our transistor here because more GM. Here less GM will be there because with respect to VDS, you can see here VDS is there. What is VOUT? VOUT equal to VDS. Right? VOUT equal to VDS. Now it's understandable. The person who
Yes,
asked
sir.
out, is it understandable now? No response. Okay. So we want to operate our transistor in saturation region. Okay. So in this point, what is a gain? Gain means okay, dou V out. I want to find the slope. So dou V out, differentiating V out with respect to the V in here at this point. So dou V out divided by dou V in. Okay, V out you already know VDD minus RD into the saturation current expression. Differentiating things. Okay, you will get this expression. So you know minus RD V in CR W by L V in minus VDS. So what is this term? This term is a GM.
GM.
Minus GM into RD. Fine. So GM is a transconductance. Just now I mentioned. So remember, it will convert a current. Current can be converted to voltage using the resistor. So GM into RD. GM is a current, voltage control current source. That current I want to convert a voltage. Resistance is added. Load resistance. GM into RD. Fine. Now, what is the current? Okay. So now what is the current direction here? Drain to source. Fine. Okay, so this current convert to here voltage. Now voltage will become negative. Yes, am I right?
Yes, sir.
Can see current direction is here. So what is V out here? Minus ID into R. Fine. So ID equal to what is ID? Minus GM VGS into RL. So GVGS is the input. So V out by V in equal to minus GM into RL. So that's what negative sign indicates the opposite polarity. That means it is common source amplifier is a inverting amplifier. Right? There is negative indicates inverting amplifier. That means you are applying the sine wave, the output will become minus sign. You apply a cos wave, output will become minus cos. 180 degree phase shift will be there. When that means plus or minus pi. Pi means 180 degree phase shift. So common source amplifier is a inverting amplifier. So negative indicates inverting amplifier. The gain is, and the magnitude of gain is GMRD. Okay, so this thing we have derived by from the large signal equation. Okay, and the large signal means with the current expression, and the current and the KVL equation. Similarly, we can derive the gain using the small signal model. So you know this is the small signal model we discussed just now. You can see this is a low frequency model. GM-VGS, R0, GMB-VPS. Okay, so in this circuit, any body effect there? Any body effect is there or not?
No, sir.
No, because source and bulk are shorter. VSB is 0. So there is no body effect. So definitely this term won't be there. So only GM-VGS and R0. Okay, so you can replace here. So GM-VGS, so VGS is, you know, this voltage. Okay, this is gate. Okay, drain. Source, so VGS is V1 or simply V in, right? GM V1. I didn't consider R0. So let's take without R0 or without channel and modulation. I first initially neglect channel and modulation. That means without R0. So without R0 means ideal this thing. Right? This is small ID. Right? This is small ID, small signal current. So what is V out will be now? V out equal to minus GM V1 into RD. What is V1? V1 equal to V in. So what is the gain now? V out by V1 minus GM RD. Fine, the same expression. Okay, very simply we derive. Okay, here from the large signal thing, okay, small signal we can very quickly find the gain. Fine. So this is due to small signal. We didn't consider the channel and modulation resistance. So now we'll include the channel and modulation resistance. We'll include R0. Source is grounded, so R0 is also grounded. Now the equivalent resistance is R0 parallel with RD. So simply in terms of RD, RD parallel to R0 will come. Therefore AV equal to 1. So due to finite R0, the gain will get reduced. So ideally minus GMRD. Due to channel and modulation reset, the RD will become RD parallel to R0. Is it fine? So similarly, we can derive this expression from this large signal equation also. You can try on your own. Take V out, add 1 plus lambda V out channel and modulation effect. Okay, then find dou V out divided by dou V in. We can find this expression from the large signal equation. From the same expression, we can find some small signal equation. Fine. So now you can understand how the small signal equivalent is helpful to find the gain, because the gain, everything under small signal parameter. Right. So for finding this gain, you want GM. If GM, we already what are the different formulas are there, right? So this is the GM is an operating point. Okay, with respect to the operating point, what is the GM? With respect to the operating point, what is R0? That means so B in, B out. Right. So this is our large signal curve. Okay, so we are operating here. So here, what is the thing? This is a DC point. V. So this is a V out point. So this is a Q point. So in this Q point, so what is GM? So what is the GM formula? Mu n C of W by L. VGS minus, so VGS is Vn. So Vn minus Vt. So once you know Vn, we can find GM. Similarly, what is R0? R0 equal to 1 by lambda ID. Here ID is here. That large signal thing. This is a DC point. So in this point, what is ID? Fine. So what are the parameters? Once GMID knows, okay, so then we can model it as small signal, because R0 is 1 by lambda ID, GM equal to in terms of some DC point. Okay, so once you know come to do thing, we can draw the small signal model. Then we can find the gain. So that's all about common source amplifier. Any doubts?
No, sir.
Is it understandable?
Yes, sir.
Okay, so I will share the material in okay, maybe this chapter 2 can yeah, I already mentioned we can download this. I'm referring the same material as in the Rajavi's course page. Okay, so you can refer the material there. You can download from there. It will be offering the same thing. You can see it is a textbook PPT only. Fine, so you can download the material from there. Okay, whenever I am taking the material on my own, I'll upload in MS Teams. Okay, so remaining whatever material I am using, that taken from there only. So,
Sir, material will not be uploaded in VTalk.
what? No, you can
Will
download
you?
from the website.
Okay, sir.
That's what first class I mentioned. No, I'm referring website also I mentioned. No, okay. So let me. Okay. All of you seeing the screen?
Yes, sir.
Okay. You go in. It's very slow now. This is home page. Okay, so go to teaching. Teaching. Yeah, go to teaching. Okay. Here. Yeah. Zip file. All of you seeing it?
Yes,
Here
sir.
only
Yes,
that all the slides are there. You can download from there. Fine. All the chapter files are there. Why you are going to upload getting VTAP every time? Everything is available here. Okay. If I am referring other than this material, I will post it in a VTAP or MS Teams. Is it fine?
Yes, sir.
Okay, so let me take the attendance and let me stop recording.